All right, I think we are at the 40 minutes past. So, good morning. Welcome to the last day of NDC London. And thank you for coming to my talk. After the last 2 weeks, I'm surprised anyone wants to hear about LLMs. I'm also a little tired of it, but we're here now, so let's strap in. So my name is Jodie Burchell. I am working as a developer advocate in data science at JetBrains. And I've been in data science for around 10 years. I actually spent a big chunk of my career in natural language processing. So the title of this talk is a question that I've had to answer myself in my career many, many times. Actually knowing when you build a machine learning model, if it's actually any good, is quite a tricky thing. And as we've entered the age of large language models, as you're going to see in this talk, that question has gotten harder and harder to answer. So just before I get into the talk, I also just want to do as a little aside, what you're going to see is a lot of links at the bottom of each of these slides. A talk like this requires quite a bit of research. Don't panic about taking photos or trying to get down those links as I'm speaking. I'm going to be showing you a QR code at the end, and it's going to take you to a GitHub repo. It'll have my slides, and I'll have all those resources. It does mean you need to stay until the end, but I do promise I'll make it worth your while. So let's go back to this question. Can you trust your models? Can you trust your machine learning models? And can you trust your large language models? The thing is, we're talking about data science, so it's in the name, it's science. This is not really a question of vibes or trust. It's nothing that vague. It's actually something much more scientific. It's a question about whether you're measuring the right thing. And to illustrate the difference between these things, I want to tell you a story that happened around 15 years ago. So in 2010, there was a social psychologist called Amy Cuddy, and she was teaching psychology at Harvard Business School. So Cuddy started noticing a difference between how her students behaved. This is part of the problem of doing a psychology degree. You start getting experimented on by your professors. So Cuddy noticed two groups. She noticed firstly, she had this group of students that were doing very well at their written assessment. But when it came to class participation, they were really failing. And they were really afraid of speaking in class. They would put up their hands like this. They sort of shielded themselves. And when they were called upon to speak, they had very little conviction in what they wanted to say. Now, in contrast, there was another group of students. They were also killing it at written participation. But when it came to class participation, they were so confident. They would raise their hands high, and they would answer with a lot of confidence. So Cuddy started to wonder, what is the relationship between body language and confidence? And could it go both ways? Could it be that rather than just their body language reflecting an underlying level of confidence, you could incite higher levels of confidence with confident body language? And this kicked off a body of research that Cuddy led into something that she called power posing. So what she got participants to do was to hold expansive high power poses, as she called them, like this, the Wonder Woman pose. And she found that participants in this group reported feeling higher levels of power. They were more inclined to take risks, and most importantly, they showed physiological changes. It's very exciting. So the participants in this high power group, they actually showed higher levels of testosterone and lower levels of cortisol. So this indicated they actually physiologically were feeling more dominant and less stressed. So this really excited Cuddy's colleagues, and it excited the wider scientific community. Cuddy got a publication on this research in the top journal in psychology. And then it hit the mainstream. Cuddy got press interviews. She got an appearance on Oprah, and she got one of the top TED Talks of all time. Remember TED Talks? It was very 2010. So Cuddy's findings spread throughout the mainstream. You had people sneaking into bathroom stalls to power pose before job interviews, or holding these poses before doing something difficult, like walking on stage to do a presentation. So Cuddy had become an absolute mainstream phenomenon. That was until 2014. Another researcher called Ava Rainhill tried to replicate Cuddy's findings, and she couldn't replicate most of them. And most importantly, she couldn't replicate that jewel in the crown of Cuddy's findings, those findings of physiological changes. Other researchers jumped on board. They started to try to replicate what Cuddy had found, and they couldn't either. And this body of evidence started to call into question whether Cuddy had found something real. The whole unhappy saga reached its peak when one of Cuddy's co-authors on the original study publicly disavowed their findings, and Cuddy's credentials as a scientist were called into question. So what happened here? What is going on? Was Cuddy a charlatan? Was she just trying to get, this press kind of circuit, this talk circuit? She got a book published out of this after all. Or was she incompetent? Was she unable to do research to the standards of her field? Well, the thing is, neither of these things were true. All of this went down when I was doing my PhD in psychology. And what happened was Cuddy was fooled by results that looked real, but they told her the wrong thing because she had measured the wrong thing. So I know what some of you are thinking. I am a psychologist, and I know you're thinking, it's psychology. It's not very scientific, so of course this happened. But this couldn't happen to machine learning. Machine learning is so much more robust. It has all those complex math and all of those really sophisticated algorithms. Well, of course, this is a trap, not so fast. So reviews have been done on a lot of papers that use machine learning techniques at the core of their studies. And it's found that in all of these fields that I'm showing you here, at least 15% of the studies could not be replicated. They found the wrong thing because they had measured the wrong thing. And as you can see from this list, this includes arguably more objective fields like genomics, like medicine, and oh yes, software engineering. We did not escape either. So this raises a really troubling question. If even experts in machine learning are getting this wrong, don't know what's going on in satellite imaging, they're getting it wrong 100% of the time, how can we be sure that we are creating good machine learning models? How can we be sure that we're creating the right, we're actually measuring the right thing? So to give you an example of one of these studies, to kind of make this really concrete, what you can see is an example of a study where they were trying to see whether 4 different machine learning techniques, 4 different machine learning algorithms, when performing a task on the same data, would get different results. And what they found is that newer and more sophisticated techniques outperformed logistic regression, which is a very old and quite basic technique in machine learning. So it makes sense, right? You would expect that something that is more sophisticated, something more cutting edge, is going to outperform something more basic and older. Except none of it was real. The authors had made really major mistakes with the way that they had measured their findings. When these were corrected for, there was really no difference between the algorithms. So these are the sort of degree of mistakes we're talking about. They seem really basic, but even experts fall into this trap. And I can tell you, in my career as a data scientist, a couple of times I've fallen into these traps as well. So let's have a look at how we might be able to assess this more scientifically, to be able to know whether we really can trust our machine learning algorithms. So in order to assess this, we can borrow some lessons from a branch of mathematics called measurement theory, which is the branch of mathematics as to how to measure things. And measurement theory tells us that a robust machine learning algorithm has 2 components. It must be reliable and it must be valid. So reliability is essentially saying that a model will give you the same results consistently. This involves a few different facets. So the first is that if you put in equivalent inputs, the model will give you an equivalent output. The same input, the prediction will be the same. This will also be consistent over time. So the same model will give you the same predictions when it's created as it will 6 months, a year, 2 years later. And then finally, different ways of assessing the same thing will converge on the same results. So say you have a machine learning model that is giving you predictions, and you have a human assessor that is also trying to predict the same thing. With a good model, they should converge on the same things. Now, validity is, on the surface, a little more straightforward. It's essentially measuring what you set out to measure. And this seems really, really basic and obvious, but you're going to see it is quite tricky to get right. So again, this has a few different facets. The first is that you have a well-defined and concrete idea of what you're trying to measure. You also, again, have this sort of convergence of related measures. So if you're measuring one thing and you're measuring something that's related to it, those scores should correlate. And again, you should also find that models that you have created in a nice, safe development environment will perform well when you release them out into the real world. So let's have a look at a very serious problem that can endanger reliability. And this is something called data leakage. Sorry about my pronunciation of data. I get comments on this all the time. You're going to have to put up with it for the rest of the talk. So data leakage, I think the easiest way to explain it is, imagine you are a professor that's giving an exam. So you have a bunch of students and you have a bunch of past exams. And in order to help those students train for this exam, what you'll do is you'll give them all of the past year's exams. But when it comes time to actually assessing them, you give them a fresh exam. So what you're then sure of is when they take that fresh exam, you're actually measuring the things they've learned. But let's say you're a bit busy, maybe a bit lazy, and you decide to recycle questions from those past exams that the students trained on. Now you run into a problem. It's no longer clear what you're measuring. Are you measuring what the students learn, or are you just measuring how well they memorized the past exam questions? So this is the problem of data leakage. It becomes unclear what you're actually assessing because you have access to training materials during test time. So this also happens with machine learning models. And a good case of this is a model called ChecksNet. Now, ChecksNet was designed to try and assess whether people have pneumonia based on their lung scans. And when it was released and they measured it, it worked super well. Great. Hooray for science. We have a super cool model, right? Well, not so fast. The problem is that when people went in to get their lung scans, they didn't just get one lung scan. They got multiple, almost identical lung scans. And when the creators of the model put their data into training data sets and testing data sets, they didn't know this. And they mixed these up. So essentially, the model had access to images it had basically seen during training at test time. It's exactly the same as the problem with the students. Essentially, you do not know what you've measured. So let's now go back to validity. So in the early days of machine learning models, assessing validity was pretty straightforward. We had models that were pretty transparent, and this made it really clear what the models were actually learning from the data. So we take the case of linear regression. This, again, is a very old and very kind of explainable algorithm. What you can see in this table is a bunch of features. These are things that are used to predict the outcome. And in this case, what we're trying to predict is how well students went on an exam. So we have things like the hours spent studying, the course level, and their current GPA. Then we have this weight column. Now, this weight column is very interesting. What it tells us is exactly what the model has learned about the relationship between each of these predictors and how well the student will go on their exam. So in the case of this 1.5 next to hours spent studying, it tells us that for every hour a student spent studying, they're going to get an additional 1.5% on their exam. This is super, super clear. It's really obvious what we're measuring here. But the problem is as we've moved into more and more sophisticated algorithms, we've moved into what we call the black box era of algorithms, where models have become more powerful, but much less explainable. So we can see this in the case of this vision model. What I've done here is pulled out the hidden states of this model, and you can see that going from the bottom up, it seems to be sequentially building up images of a cat. But I'm not really sure if that's what's happening. I've had to add a layer of interpretation to that. Or if we have this, we have this early small language model. What we can see is it appears to be learning the relationship between the words in a sentence. But again, it's not entirely clear if that's what's happening. And as we've entered the age of large language models, here we come to it, things have really gone off the rails. What we can do is only really see if the inputs appear to make sense with regards to the outputs. It's very, very difficult to peek inside these models, and we have no way of really doing it holistically. So we can see this example here. I've asked an LLM to write me a joke about cats, and it has come up with something that makes sense. But I don't know how the LLM knows what a concept of a cat is, or how it knows how to make really bad jokes. And one of the biggest problems we have now is we now have problems with model reliability. We never had this problem with machine learning models before. Once you trained the model, it would give you the exact same output for the same inputs. But LLMs don't work like this by design. They are designed to give you variation for the same input. So again, you can see this with this model. Get the same input, 2 different cat jokes. I mean, they're equally bad, but that's more of a taste issue than a reliability issue. So this brings us back to the same question we asked before about machine learning models. How can we know if an LLM is good? How do we measure the right things? How do we know if we've measured the right things? So this is going to kick off the rest of the talk, and we're going to be discussing the noisy and extremely confusing world of LLM assessment. So if you've been existing in the world for the last year and a half or so, you will have heard LLM vendors or research labs telling you how good their models are. So you might have seen papers or release materials that have some variation of the following. We've just launched our newest large language model trained with state-of-the-art GPUs, and we've improved on the MMLU by n points, beating the previous best. Sounds very convincing, right? Or maybe if you've gone a little bit deeper, you might have seen LLM leaderboards. These pit models against each other on exotic sounding measures like Winogrand or Hellaswag. But how do we know whether scoring well on any of these measures mean anything? What are these measures actually assessing? And does scoring really well, does topping the leaderboard mean that an LLM is good? So let's go a little bit deeper and have a look at the different ways that we're trying to assess LLMs right now. So I would say one of the most controversial ways to assess LLMs is to get them to complete some of the hardest tests that we have for humans. So you can see an example of that here. What we have is 4 LLMs who have completed questions from a US medical exam. And you can see they've done great. GPT-4 got 100%, and even the worst performing model still got 75% correct. Okay? So you might have remembered around the time that GPT-4 came out, this was around 2 years ago, results like this were everywhere. And this led to corresponding claims that we were going to be all replaced. We're going to replace doctors, we're going to replace lawyers, and we are, of course, going to replace programmers. But it's been almost 2 years since we first started seeing these results. We first started seeing models that could do this. And I would argue we have not seen any material progress towards replacement of anyone in these professions. In fact, we've seen some lawyers getting into quite a lot of problems because they tried to use these models to automate part of their job. So what gives? Why haven't we seen replacement of humans when clearly these models are probably outperforming us on some of our hardest tests? The issue is, and if you've seen any of my sort of previous talks about LLMs, you'll see that the issue with using benchmarks that are designed for humans to assess LLMs is that they're fundamentally measuring different things. So let's go to, say, medical exams. Medical exams are a way of assessing how well someone is going to go when they're practicing medicine. They're a proxy for assessing how suited someone is to being a doctor. And in this case, they do have pretty good validity. You can see that, from papers, we've got a couple of references there, people who do well at medical entrance exams tend to do well at med school, and if they do well at med school, they tend to do well when practicing medicine. So the reason that this works, the reason that we can use exams as a proxy for future performance is because of the way that humans learn. So humans have a mechanism called G, or general intelligence, and this allows us to generalize, to apply the same sort of skills to multiple related situations. So in the case of medical exams, what you're tapping into are things like learned knowledge or reasoning, and people who are good at applying both of these to medical exams also tend to be good at applying these to practicing medicine. So what does it mean when an LLM does really well at, say, a medical exam? Well, it means that an LLM is really good at completing the sort of questions that are on medical exams. Nothing more, nothing less. So I know you've got some doubts. You're thinking, why? Like, why can we not assume that this is a proxy for general intelligence in LLMs? And the reason for this is due to the way that LLMs are trained. So training any type of machine learning model is really cumbersome. And what it means is that the way we set up machine learning models to train is with very specific goals in mind. So in the case of ChexNet, this was simply to detect whether lung scans show signs of pneumonia or not. That is the only thing that model was trained to do. In the case of LLMs, it's a little more complex, but with the sort of LLMs that everyone is talking about, the generative LLMs, they were trained to predict the next word in a sentence. It's really all they were trained to do. So let's talk through the process of training these sort of models. What you have is a batch of the training data. And for that training data with these sort of models, you'll have a correct answer. The next word in the sentence is known. What the model will do is make some sort of prediction about what it thinks the correct word is. Then what it will do is compare it against the correct answer. And to sort of understand how this training works, these models are initialized randomly. So these guesses at the beginning are going to be random. They're going to be very inaccurate. So the model then needs to update model weights. Am I beeping? Someone is beeping. It's okay. It sounded like it was coming from behind me, so I was very confused. So the model needs to update its weights, and it then needs to do that over and over and over again across all of the training data until it reaches a good performance. So because this is so cumbersome, the way these models have been designed is with mechanisms that take the shortest path possible to get to this training goal, mechanisms like gradient descent. And it's very, very unlikely, because of this optimization, that a model is going to randomly go off, develop something like general intelligence that's not strictly needed to solve the problem, and then go to the training goal. This might feel like a slightly shallow explanation of this. I do have another talk I gave at NDC Oslo which dives into the assessment of intelligence, if you want to look at that a little bit more. But generally, that's the gist of it. Really, these models are not displaying general intelligence. They're just displaying pattern matching that makes them look like they mimic our general intelligence when solving these tests. So, we've concluded that benchmarks for humans are no good. So what about benchmarks that are specifically designed for LLMs? Well, let's go back to this table that we looked at a few slides ago. So this is an LLM leaderboard which was created by a company called Hugging Face. And up until around 6 months ago, this was one of the key ways of assessing whether open source LLMs were any good. So basically what Hugging Face would do is it would get hold of these open source models, run them against a series of gold standard benchmarks, and then basically tally up those scores, combine them in some way, and use them to rank and rate these models. But in June of last year, something rather strange happened. This very trusted table was retired, and a new one was brought in with new benchmarks. So what happened here? What happened to these benchmarks? Why don't we want to use them anymore? Well, there are a few reasons, but one of the funniest is that the gold standard label that we'd applied to these benchmarks was perhaps not as deserved as you might think. So these benchmarks, when people started going through them, were discovered to have many problems. Problems with typos, problems with incomprehensibility, incorrect answers. So I'm going to show you a few examples from these. And I really want to make it clear when I show you each of these, I haven't changed them at all. These are exactly as they're displayed in the benchmark. So we're going to start with a question from the MMLU. And this used to be such a trusted measure for assessing the performance of LLMs, not just open source, but the big ones, like the ones from OpenAI. The companies would be measuring their performance on the MMLU to 2 decimal places. So let's see a question from this. The complexity of the theory. Now, this is the whole question. I'm not leaving anything out. All right, maybe there's some more clues in the answer set. 1, 2, 3, 4. 1, 3, 4. 1, 2, 3. 1, 2, 4. These numbers don't match up to anything. This is the full information that the LLM is given. And remember, we're trying to assess whether these LLMs can solve these problems to a human level. Can you answer this question? Would you be able to guess that the answer is C? I couldn't. So let's have a look at another one. So this is from a very popular benchmark measure called HelloSwag. And the idea behind HelloSwag is you're essentially trying to see whether an LLM or a human can deduct what's happening in a setup scenario and complete that scenario. And again, I've typed this out exactly as it appears in the benchmark. Men are standing in a large green field playing lacrosse. People is around the field watching the game. Men are holding t-shirts watching into lacrosse playing, are being interviewed in a podium in front of a large group, and a gymnast is holding a microphone for the announcers, are running side to side of the field playing lacrosse trying to score, are in a field running around playing lacrosse. Now, every time I read this question, I feel like I'm having a fever dream. It is so weird. But typos and bizarre imagery aside, I'm guessing we're meant to answer that the men are playing lacrosse, but both C and D tell us this. Which is the correct one? I also want to say from HelloSwag, there were worse questions, but I couldn't put them in the slides because I couldn't read them out. They're just so broken. I encourage you to look at this paper. It's really funny. There's a lot of really good examples. And then finally, just one more. This is from a measure called Common Sense QA.
What's the answer of the previous one?
I think it was C as well. Yeah, but, you know, does it matter? So one more, this is from a measure called Common Sense QA. This is also a very popular measure. So we're off to a good start. The question actually makes sense. When a person is breathing in a paper bag, what are they trying to do? But let's not get too excited. Let's look at the answers. Warm air, continue to live, going to sleep, hyperventilation, stay alive. Now, I don't know about you, but I don't think any of these are what you're trying to do when you breathe into a paper bag. So again, what's this poor LLM supposed to do if we can't even answer these questions? And I know this section probably feels a bit like I'm cherry picking and just picking out one or two, really bad examples. 36% of HelloSwag was thought to actually have answers or questions that were as bad as the one that I showed you on the last slide. And there are probably hundreds of such really, really bad questions throughout the gold standard benchmarks. So this is one of the reasons why Hugging Face retired their old leaderboard and why they brought in a new one. These new benchmarks are better curated, they're checked for accuracy, and they have less of this sort of random garbage. So I guess the question we now have is, okay, we have these great new benchmarks. Does this mean that we've solved the problem? Does getting 100% on all of these benchmarks mean that an LLM is good? And I hope you've realized we are now halfway through the time slot, and the answer is, of course, no, because I have so much more to show you. One of the things I want to show you is a really fundamental problem, and that's actually how LLMs answer each of these benchmark questions. So LLMs have two ways in which they can answer benchmark questions. They can first be presented with a series of multiple choice options. So for example, if you would ask an LLM, what is the capital of Portugal? You can give it a number of options, and it can either tell you B or Lisbon, or some combination thereof, and you will know if it's correct. Or it can, of course, generate free form answers. So if we would ask, what is the capital of Portugal? And it tells us something like the capital of Portugal is Lisbon, then, of course, it's going to be correct. Now, you might have noticed that all of the examples I've given you so far are using multiple choice options. And that's because being able to assess whether a multiple choice option is correct in an automated way is much, much easier than if an LLM generates a free-form answer. So what's the problem? We can just use multiple choice for everything, right? Well, wrong. A fundamental problem we have with LLMs is that their performance on benchmarks is actually affected by which one of these answer types we ask them to use. So here are 3 LLMs that are answering questions from the same benchmark. And here's how they perform when they're presented with multiple choice options. And here's how they perform on the same benchmark when they have to generate a free form answer. Now, what you can see is that in the case of every single LLM, they perform worse when they're asked to generate an answer. But it gets worse than this. The problem, the real problem, is they're not actually getting the same items correct between the two answer types, which of course is a validity issue. The two answer types are measuring two different things. And what researchers believe is that multiple choice taps more into rote memorization, whereas being able to generate a correct free-form answer taps more into creativity and reasoning. We have another issue, another about convergent validity. So remember I said that an aspect of validity is that you should have, when you have two related measures, they should actually converge. Like an LLM completing one measure assessing one thing and measure assessing something related, those scores should be correlated. But we're finding this isn't actually the case. So let's have a look at this simple reasoning puzzle. Alice has 3 brothers and she also has 6 sisters. How many sisters does Alice's brother have? Now you're all developers, I know you love to solve puzzles. I'll give you a few seconds. Does anyone want to try and guess and shout out?
7.
Perfect. So let's solve it together. So Alice is a woman's name. So Alice is, of course, one of the prospective sisters. And then there are 6 other sisters. So if we add those together, we get 7 potential sisters for each of the brothers. So this is part of a suite of reasoning puzzles called Alice in Wonderland for some reason. And they're all as difficult as this. You know, you can see they're not terribly complex. And they're designed to assess basic reasoning. So what the developers of this suite of puzzles did is they got a bunch of state-of-the-art LLMs to complete these puzzles. Then they got them to complete the MMLU, which is also designed to assess reasoning. So what you would expect is we have 2 measures that are basically assessing overlapping things. So in that case, you would expect that the scores should be highly correlated. In fact, like in that sense, they should lie along this diagonal line. What they found was a pattern like this. What's going on here? What this tells us is that every single one of the LLMs got much higher scores on the MMLU than they did on these basic reasoning puzzles. And even worse, most of the LLMs were getting less than 5% of the Alice in Wonderland puzzles correct, while they were getting more than 50% of the MMLU items correct. Now this tells us 2 things. It tells us that the MMLU is probably not assessing reasoning, not in the way that it's claiming. And it also tells us that these reasoning capabilities of LLMs, if they're based on the MMLU, are probably overstated. This is the thing. These are language models. It's in the name. So should they even be trying to assess things like reasoning or other non-language problems? So let's go back to the beginning of this talk, when I was talking about what machine learning models are designed to do. Machine learning models are trained by design to have very specific problem domains. They're designed to solve very specific things. So in the case of, say, an image classification model, it's designed to just tell whether a picture is a dog or a cat or some other animal, perhaps. And in the early days, LLMs were the same. The first LLMs were actually designed to do machine translation. It's a very concrete problem. And they were applied to other things like summarization or question answering. These are very specific natural language processing problems. So in the early days, what we had was a suite of benchmarks that were designed to assess just this. They were designed to assess, like, how well can a model complete question answering? How well can it do classification of text? But as the capabilities of these models have grown, or as they appear to have grown, because I hope I planted that seed of doubt, we've come up with more and more exotic benchmarks to try and capture this. So, we've come up with benchmarks to try to see whether these models have advanced reasoning capabilities. We try to come up with benchmarks to see whether they have deep domain knowledge across technical areas. And we've even come up with benchmarks to try to assess whether these models are showing signs of artificial general intelligence, or AGI. Now, for me, this taps into one of the core validity issues with LLMs. You, as a user, are going to pick an LLM to do something specific. Maybe you want it to do classification. Maybe you want it to do question answering. Maybe you want a chatbot that can answer questions for your customers. But what you're going to be using to pick your LLM is maybe a leaderboard that assesses it across 12 different measures, none of them have anything to do with your use case. So by trying to assess LLMs and present their performance in such broad strokes, we've really lost touch with what we're really trying to use them for. There's a big gap between the assessment in the public domain and how you're going to need to be able to assess them within your application. So benchmarks are no good. So you might be thinking, is there some sort of alternative to this? And those of you in the know might be screaming at me internally right now, what about the chatbot arena? And those of you who have no idea what I'm talking about are thinking, God damn, you really like giving things weird names in machine learning. And that is also true. So the chatbot arena is an experiment presented as a website. Anyone can go to it. And basically what you do is you think of a prompt, any prompt you want to give an LLM. And what the chatbot arena will do is go away and it will pick 2 state-of-the-art LLMs to present you with 2 competing answers. And your job is to pick the one that you like best. So I've gone there and I've entered, please write me a poem about sausages. And I am quite partial to this second answer. Plump and juicy, in a row they lie, sausages waiting to satisfy. So the results of my experiment and everyone else's experiment who goes to this website are combined in something called an ELO score. And this is then used to, of course, rank and rate LLMs, and they have their own leaderboard to display these results. So the chatbot arena is seen as one of the most trustworthy ways to assess LLMs right now. People like Andre Karpathy, who's an absolute giant in this area, has come out in support of it. And in some ways it's true. The chatbot arena shows high validity because it's a direct reflection of how end users are going to receive LLM outputs. So, it's based currently on more than 1 million experiments, and those experiments are conducted by just people like you and me, who have a really broad range of experiences, of preferences, and the prompts that they're going to use. You've got ridiculous people like me coming along and asking for poems about sausages, and then you've got people asking for actual serious things. So you might be thinking, fantastic, we've solved this problem of LLM assessment. But again, let's not get too excited. One of the problems that you might have spotted is the way that you're asked to assess whether an output is worthwhile from an LLM. And the terms that the chatbot arena uses is good and bad. Now, what does this mean? What does the output of an LLM being good really mean? Does it mean that it's verbose? Does it mean that it's concise? Does it mean that it's accurate? Does it mean that it's moving, it's funny, it's witty, it's entertaining? Does my sausage poem being good mean the same thing as a resignation email to your boss being good? A eulogy for your friend being good? These are very different types of content. So the problem is we are now stuck with a low validity term in order to try and capture everything that we want LLMs to do. Basically, the reach, the application of these models has become so diverse that creators of things like the chatbot arena are stuck with such vague terms in order to assess them that they essentially become meaningless. So right now, I've been really hammering validity home, but we haven't forgotten about reliability, so let's circle back to that. So one of the problems with the measurement of LLMs is that they're trained on absolutely enormous public data sets. In fact, it's estimated that a huge chunk of the current public internet is being consumed for their training. And to kind of compound this problem, the creators of LLMs, even the open source ones, have become increasingly cagey about what is actually used for their training. So it makes it really hard for us as consumers to get a good idea of what was actually used to train that model and what it's seen before. So this might sound very familiar to you, and of course it's there on the screen. This is a data leakage problem. If you're trying to assess a model, you don't know what it's actually seen during training. So you might show it something that it's seen before, and that's essentially going to be very confusing to you. Is the model actually showing reasoning? Is it actually completing a novel task well, or is it just regurgitating something it memorized during training? So a really nice example of this circulated on Twitter around 2 years ago, around the time that GPT-4 came out. So when everyone was getting very excited about these models completing LeetCode puzzles, a researcher called Horace Hay got a little suspicious, and he started thinking, this sounds like a data leakage issue. So what he did is he went to a website called Codeforces, and Codeforces has LeetCode type puzzles. And what makes it really good for this particular experiment is that each of the dates that the puzzles were released is clearly marked. So what he did is he got a sample of 10 puzzles that were released during the training period of GPT-4. So the model could have had access to it in the training data. And he passed each of them through the model and got each of them correct. Well, congratulations, you're coming for our job, GPT-4. But then what he did is he got another 10 puzzles that were released after the model had trained. So it could not have had access to them during the training period. And these puzzles were of an equivalent level of difficulty. And this time, GPT-4 got every single one of them wrong. So it smells like data leakage. And to confirm this, another researcher, Saj Kapoor, directly prompted the model. He asked the model, which code forces is Aqua Moon and two arrays from a model that was available when, a puzzle that was available when the model was trained. And obligingly, GPT-4 vomited up the complete source. So it confirmed that it had in fact trained on these puzzles. So this illustrates really clearly that it's really difficult to trust these face value sort of tests on performance of LLMs because you just don't know what the model's seen during training. Now, this problem is compounded. This problem goes so deep that it doesn't just affect informal assessments like the one I showed you. It actually has affected the benchmarks. So a review was done of the benchmarks that the ChatGPT models have had exposure to. And it was found that dozens of these benchmarks had at least partially leaked into the training data. You can see that 75 question answering benchmarks alone had partially leaked into the training data for these models. And you can see this leakage affected benchmarks across pretty much all of the major ways that we assess these models: natural language inference, natural language generation, summarization, math, and programming. And to compound this problem further, the amount of data that is actually of sufficient quality to train and assess these models is a finite resource, and we're actually relatively close to running out of it. So the current sort of wisdom for at least until last year is the best way to scale models is to make them bigger, to feed more data in and give them more parameters. This, of course, could be changing with the announcement of DeepSeek, but definitely until last year, this was the wisdom. So you can actually see the growth in model size, and you can see that this is an exponential scale. We went from, I think it was 500 billion tokens. Let me just check my notes. We had 15 trillion tokens, 500 billion tokens were used to train GPT-3, and that was back in 2020. And this shot up to 15 trillion tokens used to train Llama 3 last year. So that is a 30-fold increase in the amount of training data. So the problem is that the amount of usable training data we think we have is around 300 trillion tokens. And if we continue this sort of scale approach to training models, we're probably going to run out of data in less than a decade, and potentially as soon as 2 years. So this is data leakage on a scale I have frankly never seen. It's extreme. What it essentially means is that you, as a lay user of these models, will have no way of knowing whether the model has seen something before that you're using to assess its performance. And really, you're going to be fooled into thinking that it's performing a lot better than it really is. And when you present it with fresh data from your customers, it's not going to perform in the way that you think it will. So let's end off this section on reliability with everyone's favorite topic, which is prompt engineering. I'm sadly not going to be telling you how to earn $1 million a year in Silicon Valley. I'm going to be talking about something a bit more depressing, and that is prompt sensitivity. Now, LLMs are wildly sensitive to the format that you put your prompts in. This changes their performance enormously. So let's look at an example of this. Let's say we're trying to do a text classification task. And what we want to do is we want to sort a passage into a number of predefined answers. So we can put the passage at the top of this template, and we can put the answers at the bottom. Or maybe we could format this template a little bit differently. So can you spot the difference between these prompt templates? They're very subtle. Exactly. Yeah, so spacing, punctuation, capitalization, these are incredibly subtle differences between these prompt templates. So they should have no influence on how well our model does our text classification task, right? Well, let's see. So what we have is a line indicating the performance, the accuracy of these models on the text classification task. We go from 0, meaning it got nothing right, to 1, meaning it got everything right. And those seemingly tiny differences in the prompt templates led to a difference of 77% between the worst performing prompt and the best performing prompt. Now, this is outrageous. Coming from a more traditional machine learning background, I can tell you, if I built a model that was this unpredictable for essentially equivalent inputs, it would be unusable. But this is very much in the fabric of LLMs. This is how they work. Just to show you, this is not a one-off, not a cherry-picked example. Here we have a number of models that were state-of-the-art around a year ago. And with these models, essentially the same thing. We have semantically equivalent inputs that are leading to between a 30 to 50% difference in performance between the best and worst performing prompts. Now, something that makes this even more troubling, and I was talking about this with Liam just before we started, is you get these performance metrics that these companies release. This is the absolute best case scenario for how this model is going to perform. It is because they have created prompt templates that are exactly tailored to how this model best responds. But you, as a user of these models, are probably not going to know that prompt template. And you're not going to get just a small reduction potentially in the performance of the model. You could be getting half as good performance or worse. So maybe I've left you feeling a little sad. Maybe you're thinking, what's the point of using LLMs? I don't even know if it's going to be good or not, so maybe I should just give up. Well, I have a potential solution for you, but it's not as sexy as leaderboards, and it's not as easy as out-of-the-box benchmarks. In fact, you're going to see it has a lot in common with the way that we've been assessing software applications for decades now. So I recommend you read the blog post that I based this on. Again, you're going to get those resources in a couple of slides. There's a guy called Hassan Hussein, and he is basically running an AI consultancy company. Very smart guy. And he was contracted to build an AI assistant for real estate agents. Basically, the idea is they wanted some sort of interface. They could use natural language and get things like house prices and contact details, things like that. So what his company did is first kind of run through. They picked a good LLM off the leaderboards. And then what they did is they built a basic prompt template to try and get the information they needed, cover all the basic functions. And initially it was working well, but very quickly as the edge cases grew, the model performance started tanking. And they started trying to create more and more Byzantinian prompt templates to try and cover this. And the only way they were really assessing it is vibe checks, like, does it seem better? And they realized this was untenable. They were not getting anywhere, they were just getting into a bigger mess. So they went back to the leaderboard and they decided to try something more systematic. So they built an assessment tailored to this application from the ground up. And the first thing that they introduced was unit tests. And the second thing they started doing was logging traces. Now this feels familiar, right? It feels a lot more like software engineering and a lot less than like, esoteric machine learning magic. And now we've got these in place. They started building higher level assessments like manual checking and A/B tests. Again, this feels very familiar. And they were able to use this information to improve on the models through more kind of LLM-y stuff like prompt engineering or fine-tuning. And then they built all of this into a rapid iteration cycle based on the feedback so they could quickly make small changes that improve the application. So let's go through 3 of the levels of assessment that Hussein recommends. So the first are unit tests. Let's see how they will work. And they work pretty much in the exact same way that they would work with a traditional software engineering application. The one thing he cautions is you can't necessarily expect a 100% pass rate because you're not dealing with something deterministic, but you can set your level of comfort with the pass rate up front. Let's see how we might create these unit tests. So let's say one of the inputs is contact information. What is the phone number for Emily Johnson? Well, what we're going to trigger in this workflow is that the LLM will create a query for a CRM, and the CRM will return the phone number. So in that case, all we need to know is, did the CRM return a phone number? A very simple approach to this is, did we just get an array of length 1? But if you know the format of the phone number, you create something a bit more robust. This is just a simple unit test, exactly the way that you would build them with any other application. You can also use LLMs to help you generate test cases. So let's say you want to cover this functionality of retrieving contact information. So you can get the LLM to come up with fake contact information to add to your CRM. And you can also get it to come up with corresponding user prompts. Now, of course, you could also use AI code assistants to help generate the code, but you still need to do this the old-fashioned way. You still need to use your brain and think about, is this actually going to be appropriate test cases for my application? So an approach like this has high validity because we are clearly defining what we're measuring and we have a robust way of assessing that. So let's move on to the next level, and this is where Hussein recommends getting humans in the loop. So he recommends having a look at the traces, which in the case of this application are going to be the multi-step interactions between the LLM and the rest of the system, including the user. So what he recommends is taking a representative sample of those traces across all the things you want your LLM application to be able to do, and just get someone to rate them. Are they doing what they're supposed to do? Seems like a lot of work, it is, but the good news is once you have a good data set, you can start automating it to an extent. So you can get another LLM to do the same thing, and because you've got this data set, which is your gold standard, you can check whether there's agreement between what the LLM is recommending and what your rater has recommended. And this is an approach with good reliability, because you're looking at agreement between a human rater and a machine rater. And then finally, of course, there's A/B tests. There's always A/B tests. So once you get to the stage where your LLM is ready to go out to your end users, you can start experimenting with different things. You can have a look at whether the original LLM you picked is actually the best one for your use case. You can play around with prompt templates. And you can also look into potentially fine-tuning an LLM to get a bit more bang for your buck when it comes to the model that you're using. And of course, this has high validity in the same way that the chatbot arena has high validity. You are directly testing whether your system will be well received by your end users. And potentially, you might be able to tailor your prompts a bit more for your application. Maybe it'll lead to higher reliability, but not sure if that's the case. So let's go back to the opening question. Can you trust your LLM? The answer is yes, but there are no shortcuts. All of this stuff that you're hearing in the media about how good these models are, it's not going to be any good for you when it comes to assessing your specific use case. You're going to have to do things the old-fashioned way, the way that we've always done it. You're going to have to define concrete use cases. You're going to have to carve out exactly what you want that model to do and not do. And you're going to have to, as always, build well-defined, well-monitored, valid and reliable assessments in order to see whether it's doing what you need it to. So that brings us to the end of the talk. Here is the QR code if you want to chase up on the resources or on the slides. And here are my socials. I would love to keep in touch. And I think we have about 5 minutes if there's any questions. Thank you very much.
I read something recently saying that we're almost running out of training data.
Yeah.
And I heard a theory that we start using synthetic data in models, and I wondered what your thoughts are on that, because that just seems crazy to me. That just seems using made-up stuff.
I'm so happy that seems crazy to you. So the question was, we are close to running out of synthetic data. Oh, Liam?
I just want to add to this because this is against, on top of, on a different subject to the LLMs. NVIDIA is saying you can't train self-driving cars because it's too expensive to send them out on the roads. We'll create fake environments with our chips to give them the training set data for their cars, which is even more scary than creating fake text to me.
Yeah. So this is a great question. So the question was, because we're coming close to running out of training data, should we use synthetic data? So there's actually been experiments already on whether we should do this, and it's shown that model performance degrades actually quite quickly as you start introducing more and more synthetic data into the training set. The reason for this is LLMs are basically statistical averages. So they will take, say, all of the information you have about, let's say, I don't know, a bird, this particular species of bird, and it will average it into something that is sort of like the middle of all the information it sees. So what this does is it reduces variance. Variance is a very, very important concept when it comes to building robust models, because it's essentially able to see a lot of representations of how a thing can exist and be able to predict for it better. If it's just presented with an average, like a perfect use case or something that doesn't have a lot of variance, it underperforms. So this is why there's no shortcuts, no free lunch in machine learning. Oh, I think you're almost exactly the same time, so.
Yeah, just following on from that, are we getting to a stage as well where it's difficult to just, we're saying we shouldn't, it's not good to train on synthetic data sets, but if we're basically taking everything on the web and chucking it into these models, a lot of that is now generated from models itself, so we can't tell what's synthetic data anymore in that situation.
Yeah, and so two parts of this question. So just to repeat the question for everyone, basically more of the public internet is becoming flooded with synthetic data, synthetic text data. This is true. So again, I've read some stuff about this being a concern. Firstly, I want to establish there is no reliable way to automatically distinguish generated text. You can get a feel for it if you do it manually. I think you've all felt that ChatGPT vibe, but there is no algorithm that can detect this. And yes, this is a concern, that we're essentially polluting the sources. I think this is probably one of the reasons why the amount of usable data is said to be limited, because they're probably limiting it at a certain period of time, like pre-2023 or something like that. Yep, sorry.
You had a slide previously, I think, where you were talking about how models, I guess machine learning models were trained earlier on specific things and you assess those specific things.
Mm-hmm.
With LLMs, there were some specific tests or you were assessing some specific things, and now people are expanding that.
Yes.
Given we kind of know how the LLMs are built, does it even make sense to expect an LLM to be able to have general reasoning or something like that? Or is it just, people are just have wishful thinking about what they might do, or they imagine something's going to emerge and it's going to be a better place because of it?
Yeah, so to repeat the question, are people just thinking wishfully that, I don't know why I said it that, having wishful thinking that LLMs are showing anything beyond language capabilities due to what they were trained on? I would say the short answer is yes. It's very confusing when you read about this. But one of the most compelling things I saw last year is some researchers from Apple released this paper. I recommend everyone reads it, it's beautiful. Ars Technica did a great write-up on it, which is talking about all of this sort of supposed reasoning that you're seeing in this specific test, which is about kind of word puzzles for math, which is designed for grade schoolers, what they call grade schoolers in America, I think like year 8 here. It's just pattern matching. If you change seemingly innocuous variables, it cannot answer equivalent puzzles that it can from the original set, because again, it's probably data leakage, And when you change it enough, it can't match to something that looks similar enough in the training set. So my feeling at the moment, but I don't want to be like, yes, this is definitely the answer, is that a lot of it is an illusion. These so-called emergent capabilities that people are saying happen are really just artifacts of how we assess. Sorry, Denny's just one at the back first, and then I'll come to you.
So with the data leakage becoming more and more of an issue,
Mm-hmm.
how do you see companies improving their models or adapting around it?
So part of the way that assessment has changed a bit, and I forgot to mention this bit, is a lot of the newer generation of benchmarks, like the ones used in the redone Hugging Face leaderboard, aren't public. So if they're private data sets, this gives you more assurance that they haven't leaked, they can't have. Part of the problem, though, is you can get a sense of what sort of questions will be on these assessments, right? And so potentially companies can internally create data sets that look very much like it. And then when they purport really good performance, yeah, so it's just a suspicion I have, but I think that some of the good performance you're seeing is because the models are deliberately being tailored for the assessments. So it's not leakage per se, but it's something close to it. Denny, and I think that must be the last question.
Maybe more controversial and difficult question, but how do you measure the truth? Let's say in the past, different philosophers have different answers for the truth, and in these times also different religions or beliefs people have are different what's true or not. So
Yeah.
how do you handle this, the truth?
This is a really good question.
Difficult one.
Yeah, so the way that I guess assessments have been structured is around things that do have true or false answers, right? So it's around things like math puzzles or a reasoning puzzle that you might give to medical students or whatever. I think, yeah.
But even there, can you ask yes or no questions that are completely have other visions from people? For example, if you ask some people, does God exist, or was Jesus real, or something out of you is the God, or does the law of attraction exist or not? So these are kind of yes no questions with other stuff.
Yeah, so I would sort of say this has two components. So we're kind of talking about like, how can you assess the truth of some things that LLMs say? Firstly, this taps into hallucinations. No one really has a super good way of assessing them across the board, although there are some measures and they're very interesting. I would say when you're talking about core assessment of LLMs, they do tend to be very concrete because they have to be. So there are right and wrong answers. But when you're talking about the way people talk about assessing them, like let's say leaders of certain large companies running AI software, we'll talk about things like, oh, I can't wait until this model can tell me physics facts I don't know. You're like, what are we even talking about here? When we talk about AGI, what are we talking about? No one knows how to assess this. So there are things that we know how to assess. These are tied into what I've talked about, but you can see there are still so many problems with this. Then we have this additional layer where people are talking about things you can't even know if they're correct or not. And they're talking about how they're going to trust in the model giving them those answers when we don't even know if the models can reliably tell us like a recipe for chicken because sometimes they hallucinate. So yes, I don't really have an answer, but I think try not to listen to 90% of what you hear people say about LLMs would be my takeaway. And go read that amazing paper by Apple. This would be my takeaway. So,
is the amazing talk by Apple on your...
let me check. Let me check. Wait.
It was out just like 1 week before you presented this talk.
Or what's the keyword we need to...
Yeah, Apple Reasoning Ars Technica. Search for this.
Apple Reasoning Ars Technica.
Yes. Yeah. That'll.
And you will find the Ars Technica article, but that will guide you to the paper.
Yeah, the paper's a little dense. I think Ars Technica did a really good write-up on it, and that should be enough.
Okay, so that's the summary of the paper.
Yeah.
Yeah, exactly. Yeah. And I would love to continue chatting with you. I'll be around during lunch, but I think I need to give the room up now because I've already run over time. Thank you so, so much.